what we're going to turn our attention to is calculating the area under a curve, right? And so we'll start off with a function that's defined on an interval from a to b, and so we can evaluate the function at every value on this interval. And then basically what we want to do is we want to compute the area that's underneath the graph of that function but above the x-axis on that interval from a to b. All right, and so here's the basically the way that we go about this. And let me open up here's the way that we go about this. All right, we start off by dividing this interval from a to b into an equal number of parts. I've divided into n is equal to 3 parts, and then on each part we select a point. Here I've selected the midpoints, and then I evaluate the function at each midpoint, which gives me a point on the curve directly above that midpoint of each interval. And that determines the height of a rectangle. So if I multiply the height, that would be the y-coordinate of this point on the curve, by the width of this rectangle, all right, that would give me the area. I do that for each of the rectangles. I get an area for each of them. If I total that up, I get the total area of those rectangles. Now, if I can do that and let the number of rectangles grow, the total area of the rectangles becomes a better and better estimate for the area under the curve. And if I would take the limit as the number of rectangles goes to infinity, that value would be precise. I would get precisely the area under the curve. And so that's the idea. So what we want to do is we want to start with an example here. And I'm going to look at this example. This is going to be the example is basically the function that we're looking at is x squared, and our interval starts at 0 and ends at 3. I'm going to start by calculating a sum where n is equal to 3, just so that you get the idea of what's happening here. Notice that n is equal to 3. I'll be using 3 rectangles. The left end point of the interval that I'm calculating the area over is a, which is 0, okay? So I'll say a is equal to 0. We call the right endpoint b, and that's 3. So I'm going to divide this into 3 equal parts. 3 equal parts. Now, if I divide that into 3 equal parts, okay, well, then the width of them is going to be, well, in general, it would be b minus a over n. In this case, 3 minus 0 over 3, which is 1, and we call this value delta x. Delta x is the width of this first rectangle, the width of the second one, and the width of the third one. These are each delta x. Okay. All right, in this case, delta x is 1. Now, in this interval, what I'm going to do is I'm going to use the left endpoint to determine the height of the rectangle. So on this first interval, I'll have, by the way, I should say that these division points, I would call this first one x sub 0, and that's the same thing as a, and that's 0. The second one would be here. That would be at 1, because each of this is delta x is 1 unit big. So I'll call x sub 1 be 1. X sub 2 will be this one. That'll be 2. And x sub 3, x sub n was the last one. And so that would be equal to b, all right, which is 3. Remember, n is equal to 3. Okay, now out of each of these subintervals, I'm going to select a point where I'll evaluate the function. I'm going to choose the left end point out of each one of them. So I'll call this first end point, the selected point, x sub 0 star, or I'm sorry, x sub 1 star, since it's out of the first interval, and that'll be 0. And then the next one, x sub 2 star, the one out of the second interval, is the left end of the second interval, x sub 2 star be 1, x sub 3 star, the left end of the third interval, is going to be 2. And now what I want to do is I want to evaluate the function at 0, which of course is 0, at 1, which of course is 1, and at 2, which of course is 4. And see, that gives me a point on this curve. I have here 0 for x and 0 for y. Then 1 for x and 1 for y would be this point. And then this point would be 2 for x and 4 for y. Okay, so what these points are going to do is determine the height of the rectangle. So this rectangle, first rectangle, is going to have a height of 0. It's going to be the, let's see, the height times the width will be 0 for the height. All right, the width is delta x, which is 1. All right, and that's 0. Rectangle 2, height times width, that will be, well, the height here is 1 and the width is 1. 1 times 1, that will be 1. And rectangle 3, all right, the height is 4 and the width is 1. Height is 4, width is 1. And so that would be 4. Okay. And so now if I total up these rectangles, the total area of these rectangles is going to be, well, 0 plus 1 plus 4 is 5. And we call that r sub 3 is 5. That's the total area of these rectangles, which would be roughly, and it's very roughly, the area underneath this curve. All right, now what I want to do is I would like to do the same thing, all right, but I'm going to use right-hand endpoints, all right, and so in this case, so that I'll get a bigger estimate, but then I'm going to let the number of those right endpoints go to infinity. So I'm going to have to use just simply a value of n. I can't call it 3 like I did in the last example. It's just going to be n. Let's see how this would work. Let's do this again, and I have this here. So let's say that we have just a value of n. Our delta x, our width of each of these, delta x, is going to be b minus a over n. That's going to be 3 minus 0 over n, or 3 over n. Okay? All right, the place that I'm choosing is the right endpoint of each of these. So x sub 1 star is going to be, well, I start at 0 and I'm going to have to add delta x. So 0 plus 3 over n. X sub 2 star is equal to, well, 0, and then I have to add 3 over n delta x twice. So 0 plus 2 times 3 over n. And then x sub 3 star for this third rectangle, x sub 3 star be 0 plus 3 times 3 over n, and so forth. For an arbitrary one, x sub k star, if we follow the pattern here, is going to be 0 plus k times 3 over n. Okay, so we have that. All right, so now our function values, well, f of x sub 1 star is going to be 3 over n squared. F of x sub 2 star is going to be 2 times 3 over n squared, and f of x sub 3 star will be 3 times 3 over n squared. Okay, and so on down the line until I get to this place. F of x sub k is going to be k times 3 over n, and I'll square that, and that will be, of course, 9k squared over n squared. So we'll have that. So that would be the height. This would be the height of the kth rectangle. All right, 1, 2, 3, all the way out to k, kth rectangle. All right, so the height is is 9k squared over n squared. This is the height. Then I have to multiply this by delta x, which is 3 over n. So I have the height times the height times the width. So that'll be the area. And then I'd have to sum these as k goes from 1 to n. And this expression is what sometimes your book, I believe, calls r sub n, the sum of the n rectangles that we've used. All right, so let's simplify this a little bit. What are we going to have here? We're going to have, this would be the sum as k goes from 1 to n of, well, 9 times 3 is 27, k squared over n to the third. All right, and now what we want to do is we want to take the limit as n goes to infinity of r sub n, of the total of the n rectangles, but we let the rectangles get to be more and more numerous. That's going to be the limit as n goes to infinity of 1 over k, of the sum, I should say, as k goes from 1 to n of 27 k squared over n cubed. All right, now the 27 is a constant multiplier, so I can take the 27 out. I'll have the limit as n goes to infinity of 27 times, now there's one more thing, the n is constant. It does not change from term to term to term. All right, the only thing that changes from term to term to term in this case is k. So I could take the n out, n cubed, but it's in the denominator, so I have that, times the sum as k goes from 1 to n of k squared. Okay, and now this will be this 27 factor that we can take, when we take the limit, I can take the limit as n goes to infinity of 27 times the limit as n goes to infinity of 1 over n cubed times the sum as k goes from 1 to n of k squared. And this is a limit of a constant, so that's just 27. This one is one of those special limits. This one turned out to be 1/3. And so this would be 27 over 3. It'll be 9. So there are 9 in this figure. There are 9 square units. There's 9 square units under this. Let's see if I have the figure. So there are 9 square units of area in that, underneath that curve there. Okay, and so this is how we do this. We won't do this very often. We'll have a slicker way to do this in section 5.6.